Good morning, class. We're looking at college algebra practice test number 3, covering chapters 5 and 6. Here's chapter 6, exponential and logarithmic functions. What I want to remind you is extremely important because when you take the exam, remember the exam is as though you're taking it on campus, which means you pledge to your honor that it's closed notes, closed book, closed PowerPoints, you name it. There is nothing you can use. You may use a scientific calculator. In some cases, you may use a graphing calculator. All right, find the formula for an exponential function that passes through points 0, 2000 and 2, 20, where f of x is in the format a b to the power of x. So all you have to do, plug in, you have two unknowns, a and b, and you have two pairs. So in this, replace the x with 0, y or f of x with 2000, then do it with 2, x is 2 and y is 20 for f of x. So 0, 2000, that means f of 0, that means a b to the power of 0 is 2000. The second point, 2, 20, that means f of 2a b squared is 20, and this is 1. So a is found to be 2000. So we can replace the a into this formula and say f of x is 2000 b to the power of x. Now the second part, ab squared, means 2000 b squared equals 20. Divide both sides by 2000, you get 1 over 100. When you take a root, b has two answers, positive and negative 1 over 10. Remember, in the case of an exponential, the base must be positive and it can't be 1. So negative 1 over 10 is out. And you replace it and you say f of x equals 2000 times 1 over 10 to the power of x. Liz deposits $10,250 into an account that earns 4% compounded interest. How much will the account have at the end of 10 years if it's compounded monthly? And I'm reminding you of the formula. A of t is p times 1 plus r over n to the power of nt. So this is the amount of p, or principal. R is the rate, in this case, 4%. T is the time, in this case, 10 years. So what is n? N is the number of compounding per year. If it's annual, it's 1. If it's monthly, it's 12. So we write the given. P is $10,250. R is 4%. T is 10 years. And now, because it says monthly, we should know n is 12. But for now, let's plug in everything we have, ignoring the n and just keeping the n intact. So 10,250, 1 plus 0.04 over n to the power of n times 10. So this is a general case when the time is 10. In this case, part A, monthly means n is 12, and we are going to replace it. course, 12 times 10 is 120, 0.04 divided by 12, added to 1, raise it to the power of 120 times 10 to 50. It gives you $15,281.03. By the way, of course, you put it into a basic calculator. Because we are dealing with money, we go with 2 decimals. In other words, you have the third one and you make a decision about the second. And we're going to repeat the question. However, in this case, how much will the account have at the end of 10 years if it's compounded weekly? So we use the same formula here. N is 52 because it says weekly. You have everything here. Replace the N with 52. That means 520. And 0.04 divided by 52 plus 1 to the power of 520 times 10,250 gives us a little bit more, $15,288.85. It's more because it's compounded more often. How much will the account have at the end of 10 years if it is compounded continuously? The formula, as you recall, A of t is P e to the power of RT, and A of 10 would be P 10,250 e to the power of R 0.04, T is 10. And the product of these two, of course, is 0.4 e to the power of 0.4 times 10,250. This is even more, a little bit, $15,291.20 because it's compounded continuously. What is the doubling time? When you have an exponential growth, you could discuss doubling time. If you have an exponential decay, half time. The concept of a doubling time is very simple. How long does it take for something, either population or investment, to double in size? And to do so, P, which represents the initial value, it could be the initial investment or initial population, will become 2P. So you don't need to know what's A of t. So 2P. And of course, we cancel out the P from both sides. We take a natural log of both sides because anytime you have an exponential that you want to solve, you want to get to the exponent, you take a log. Because the right side has the base e, you take a natural log of both sides. Now, ln2 is ln of e to the power of RT. So let me just put that in front of it here. So ln2 is ln of e to the power of RT, and that gives you RT. So the time that it takes to double up is ln2 divided by the rate. Rate happened to be 0.04. So it's a little bit more than 17 years. And I put a lot of decimals. Normally for a case like this, they ask you how many decimals to use. But this is the exact answer, everybody. Okay. For the sake of argument, if we go back here, if the R, the rate is missing and the time is known, you can say R is ln2 divided by t. Use the graphs shown to answer the following. All of these functions have the form of f of x, a, b to the power of x. And remember, the base can't be 1 and must be positive. Which graph has the largest value for B? Which graph has the smallest value for B? B is the base. The larger the base, the faster the function grows. The larger the base, the faster the graph grows. And to have the largest, on the right side, the numbers are larger than 1. Right-hand side, RHS. The base is larger than 1. On the left-hand side, the base is between 0 and 1. Since we want the largest, we look at the right-hand side. And we look at the right-hand side. This is on the right side. This is on the right side. This is on the right side. I hope you recognize D is the closest. So which one is closest to the y-axis is D. So closest. So to answer that, let me remind you of a couple of things. Y equals a to the power of x. A is positive, the right side. A is between 0 and 1, the left side. For example, if this is 2 to the power of x, this is 2 to the power of minus x, or 1/2 to the power of x. This is how you look at it, that you say a is between 0 and 1, okay? So another one that you want to know, that if the base is 2 versus the base being 5 and so forth, when the base is larger, on the right side, it's closer and closer to the y-axis. But on the left side, as it's the smallest. So with that being the case, look at all of these graphs are in the form of y equals ab to the power of x. This has the y-intercept of 0, 1. By the way, domain is all real numbers, range from 0 to infinity, and the x-axis is the horizontal asymptote. So 0, 1, which is the same here. This one is 0, a. At x equals 0, b to the power of 0 is 1. So whatever the number is in front of b to the power of x. So to give you an idea. And so closest to y-axis on the right side, in this case would be this one, right? In this case, and let me erase my board. In this case, there are 3 on the right side. So D is the closest one. So graph of. Which one has the smallest value for B? On the left side, okay, the one which has the largest, the smallest value is closest to the y-axis. So on this side, we have this one and this one and this one. So the green one, graph of C. So closest to y-axis on the left, graph of C. Which graph has the largest value for A and which one has the smallest value for A? And as I mentioned, the y-intercept for this function has this one 0, 1 because there's nothing in front of it. This one 0, a because A is in front. Okay. So we let x be 0. The y-intercept has the coordinate 0, comma A. And so largest A, that means largest y-intercept. So look at all those y-intercepts. Which one is the largest? Clearly, this is the largest one. So the green one, graph of C. Which graph has the smallest? Again, this is the y-intercept, this is the y-intercept, this is the y-intercept. The smallest one is this one, and that would be F. Use transformation of the graph of f of x equals 2 to the power of x of the function below. State the horizontal asymptote, domain, range, and so on. So this is a general graph, a basic function that you're supposed to know the graph. Y equals 2 to the power of x, or 3 to the power of x, or 5 to the power of x looks similar to that. In this case, we are, as I mentioned in the previous page, when A is larger than 1, the graph looks like that. So if I change it to 5 to the power of x, 8 to the power of x, 10 to the power of x, generally speaking, looks like that, with the y-intercept at 0, 1. Okay. And domain is all real numbers, range is 0 to infinity. Here's the horizontal asymptote. So that's for the basic function. We should know the graph. Clearly the y-intercept at 0, 1. Now we want to change the x to minus x. So that means reflection with respect to the y-axis, or across the y-axis. So it looks like that, which we have the same y-intercept of 0, 1. That doesn't change. And the function is 2 to the power minus x. And as I mentioned the previous page, this is the same as, it's important to notice that. One half to the power of x. So this one, A is positive. This one, A is between 0 and 1. So A must be positive in all cases. A can't be 1. In this case, A is any number larger than 1. In this case, between 0 and 1, for example, 1 half. So 2 to the power of minus x is the same as 1 half to the power of x. So what do we notice? Horizontal asymptote for this one was the x-axis, the same thing here. And the equation of the x-axis is y equal to 0. Back to this one. Domain is all real numbers from negative to positive infinity. Remember, domain means try to break it along the x-axis. The same thing. This one and this one have the same domain. Range for this one from 0 to infinity. Break it along the y-axis. The same thing. The same range. The difference is this is an increasing function. This is a decreasing function. So increasing. But this one is a decreasing function. All right, so 2 to the power of x versus 2 to the power of minus x. And now 2 to the power of x plus 1. So we go back to this basic function we should know. Plus 1 means move it up by how many units? 1 unit. So shift up by 1 unit. When we shift up by 1 unit, it changes the location of the y-intercept. It goes down to 0, 2. The horizontal asymptote goes up by 1. So this is how it looks like. Y equals 2x plus 1. The horizontal asymptote has changed. The y-intercept has changed. It's 0, 2. And the horizontal asymptote has the equation y equals 1. But the domain, again, if you cut it along the x-axis, it still gives you negative to positive infinity. But the range has changed. The range in these two cases, 0 to infinity, the range starts from here, 1 to infinity. So for this function, f of x is 2 to the power of x plus 1. Horizontal asymptote has changed to y equals 1 from y equal to 0. Domain hasn't changed. Range has changed from 0 to infinity to 1 to infinity. The y-intercept of 0, 1 has changed to 0 to 2. So if you look at this basic elementary function and these two transformations, that gives you a lot of information about exponential functions. Consider the function f of x equals 4 to the power of x, right? A function that results from the given transformation. Shift f of x 3 units up. So f of x, just add 3. Shift it up by 3 units. Shifted left by 5 units. So you're going back to original function. Shifting to the left and right. Okay, if you want it to the left, you add, and to the right, you subtract. So you add 5. So 4 to the power of x plus 5. Reflected about the x-axis. That means the y must change. That means you put a negative sign in front of 4 to the power of x. I'm just giving them different names. Now, same thing, but this time reflected about the y-axis. So change the x to minus x. So this time 4 to the power of minus x. The graph below is a transformation of f of x equals 2 to the power of x. Write an equation for the graph shown. So as I said, this is considered an elementary function. We should know the graph. And we should see the transformation. For example, this one seems to have a y-intercept at 0, 2. That's one thing that we observe. There seems to be a horizontal asymptote with the equation 1, 2, 3, y equals 3. Y equals 3. That's what we observe. Okay. We also know the function f of x equals 2 to the power of x looks like that. Okay, this may not be to scale, but generally speaking, that's the case, where this one obviously is 0, 1. Now, in a matter of comparison, we notice this seems to be reflecting with respect to the x-axis. So you put a negative sign in front of that, and reflection across the x-axis gives this graph. It looks more like that. Okay. And 0, 1 now goes to 0, negative. Of course, this one or this one makes no difference. They have the same horizontal asymptote y equals 0. And we notice this is y equals 3. So y equals 0 is the asymptote for both of these. But this one is y equals 3. That means this must be shifted up by how many units? By 3 units. So if we work on this and take it up by 3 units, looks like that. And so this is the y-intercept 0, 2. This is the horizontal asymptote y equals 3. As I mentioned, 0, 2. Everything seems to be fine. So now, what is the equation? So same equation, we took it up by how many units? 3 units. So same equation plus 3. So h of x, we call it, give it any name, because we call this g of x. H of x is negative 2 to the power of x, the same one, and shifted up by 3 units. Now, what you should do if you just plug in a few easy points that you see into this, that's how you check it, obviously. This is easy to check. Okay, so if you plug in 0, you get minus 2 to the power of 0, which is uh, minus 2 to the power of 0. H of x equals, I should say. So the equality is missing. So you get 2 to the power of 0, which is 1 with negative, is negative 1, and 3 becomes 2, as you can see that. All right, so that's pretty straightforward. Now, what about log functions? If b is larger than 0, the base, and b is not equal to 1, y equals log x base b is equivalent to x equals b to the power of y. If you look at this one, x equals b to the power of y, or y equals log x base b, they have the same exponent y and the same base b. Now, log x base b equals y. First, I want to explain the meaning of log to everybody. I want to remind you of that. Log means finding an exponent. Okay. So if the question is, so 2 to what power is 8? Let's call it question number 1. It's equivalent to question number 2, log base 2 of 8 equals what? They have the same answer. As you all know, 2 to the power of 3 is 8. So log is simply an exponent. If we understand that, everything else will fall into place. So when we look at this one, the arrow will help us see that this becomes b to the power of y equals x. So if you follow the arrow, you're in good shape. So for a general case, y equals log x base b means b to the power y equals x, going from logarithmic format to exponential format. These are the properties. I want to discuss those properties quickly because then we see the transition from this general case to a specific case. So first and foremost, take a look at this arrow. Let me use a b to the power of 0 is 1. B to the power of 1 is b. B to the power of x is b to the power of x. Now, these two together refer to the fact that logarithmic functions and exponential functions are inverse functions. This is log xy base b is log x base b plus log y base b. This is called the product rule. Quotient rule, power rule. Quotient rule, log of x over y equals log x minus log y. All of them have the same base b. You have to mention base b. Log of x to the power of n is n log x. Both of them have base b. So, product rule, quotient rule, power. If we go to common law, y equals log x, we don't write the base. That means 10 to the power of y equals x. And so obviously, we are going to lose the base for all of this. So I start from the bottom. This becomes basically log of x to the power of n is n log x. So 5, 6, 7, you lose the base. Number 1, you lose the base. I want to discuss those three so you see how we make transitions. The rest of them just lose the base. For this one, when you write log, the base is 10. And remember, this says if the base and the argument is the same. So this becomes log 10. I hope you see that. Remember, when we write log, the base is 10. What about this one? You write log, you don't write the base is 10, so 10 to the power of x must be x. What about this one? Remember, the base is b, so you got to change it to 10. And you get the following. So I hope you see the transition. Next, natural law. When we say y equals ln x, we mean the base is e. We don't write the base. And what happens in those cases? Let me erase this. Now, first and foremost, everything changes to ln. This you just make it ln1. This you make it ln x, y is ln x plus ln y, and the rest of them. So numbers 1, 5, 6, 7, just change them to ln. I want to discuss number 2. So what happens to this one? It says log b base b. The moment you write ln, you know the base is e and it must be the same. So ln of e must be 1. What about this one? Because you're going to write ln, right? Then it has to be e to the power of x because the base b is e. And what about the last one? The base is b, so you have to write the base e. Log x base b becomes ln x. So that's the transition. I hope it makes sense to you. Again, The point is, if you understand this general, you can go to a common log or a natural log. Because exponential and logarithmic functions are inverse functions, for example, y equals e to the power of x and y equals ln x are inverse, they must be symmetric with respect to the line y equals x. This is known as the change of base formula. Log x with any base b is log x over log b with any base, for example, base a. However, we either go with a common log or natural log for the sake of calculation and calculators. This one, if you do the cross product, you get log base a of b times log base b of x equals log x base a. Notice the last argument becomes the argument of the result. The first base becomes the base of the result. So this is the cross product. Also, this information, what are we getting here? And I'm going to start with the red one. Red one means this. X-intercept is at 1, 0. Green one says if x is between 0 and 1, natural log must be negative. Blue one says if x is larger than 1, ln x must be positive. Okay. Again, what are we trying to do here? You should know the graph of y equals e to the power of x, or remember 2 to the power of x or 5 to the power of x elementary functions, or ln x. You should know how they look like. It's very straightforward. Let's rewrite each equation in exponential form. In other words, we want to go back and forth from one format to the next, everybody. Okay. And I'm reminding you of some of the formulas here. For example, here, we're going to say 5 to the power of q is m. Here, the same format. Let me actually do this. The same thing here. And remember, the base for ln is e, so e to the power of z is v. Same thing here. log, no base, that means common log. The base is 10, so 10 to the power of t must be w. So basically, we are using that. Now going back, rewrite each equation in logarithmic form. The reverse process. Remember, we should be able to go from left to right or right to left. So when you have it in an exponential format, the result, okay, is your argument. Log of the result, y, the base 3 must be x. The base is e. So log becomes ln, back and forth here. ln of the result, ln of h, must be the exponent k. Now, I wrote this for common log. Please understand this is not a common log because the base is not 100. So log of the result, log of b, base is 100 equals the exponent a. So we don't want to make a mistake here. So the bottom line is being able to go back and forth, everybody. And it's really not that big of a deal. Again, logarithmic format in general with base b, exponential format. Logarithmic format with base e, general exponential format. Logarithmic format base 10, exponential format. So we should be able to go back and forth. We are going to move on. State the domain vertical asymptote and the end behavior of the function f of x is log of x minus 7. We don't have any base. That means common law. It doesn't matter. It looks like a basic log where the base is larger than 1. Please understand the base can't be 1 and the base must be positive, right? Base, let me remind you. Base can't be 1 and base must be positive. If the base is larger than 1, looks like this, everybody. Okay, in other words, and as you recall, when we did even y equals ln x, looks similar to that because the base is is about 2.718 and it continues indefinitely. It's an irrational number. So if we have log of any base that is larger than 1, log base 2 of x, log base 5 of x, log base 8 of x, or in this case, log base 10 when we don't write the base, they all look similar to this, okay? Now, the larger the base, the smaller the value of the y, and therefore the closer to the x-axis. I want you to know that. In any way. So that's the way it looks like. And of course, we have the x-intercept at 1, 0. Now, x minus 7 indicates that it's been shifted to the right by 7 units. So you move this 7 units to the right. So we have originally the x-intercept at 1, 0. Now the same point, 1, 0, the same point goes to the right by 7 units. So 1 plus 7 becomes 8, 0. Now going back to the original one, the vertical asymptote is the y-axis, or x equals 0. The vertical asymptote now moves by 7 units to the right And so the VA or vertical asymptote now has the equation x equals 7. So going back to this, the domain is from 0 to infinity. 0 is not included. The range is all real numbers. So what happens to the new one? The range remains unchanged from negative to positive infinity. But the domain, as we shift it to the right, is from 7 to infinity. So domain 7 to infinity, range of both functions remain unchanged. So what is the end behavior? Go back to this one. When x goes to positive infinity, so does y. But in this case, when x goes towards 0 from the right, it goes to negative infinity. For this one, when x goes to infinity, y, that by y we mean f of x goes to infinity. But as it goes to 7, towards 7, but 7 actually from the right of that, then it goes down to negative infinity. So we write, as x goes to 7, f of x goes to negative infinity. As x goes to infinity, f of x goes to infinity. This part and this part. Now, this one I want you to pay attention. We really have to write x, and this is what we discuss in calculus. As x approaches 7 from the right, this means from the right side. If we put negative 7 from the left side. So from the right side, because from the left side, if you look at the domain, from the left side, the function is undefined. So this is understanding the graph. So let's recap. This is the general graph of elementary function y equals log x with any base that is larger than 1. In this case, more specifically, base 10. Domain from 0 to infinity. Let me just write that for this function. So domain for this function is from 0 to infinity, okay? And the VA is the y-axis, x equals 0, okay, for the basic function. So if I have log x base 2 or base 5, it's the same thing. And the shifting gives us new stuff. All right, let's move on to the following. Part B, g of x is ln of 2 minus x. Let's see what happens here. Again, we start with the basic function y equals log x, in this case, more specifically, y equals ln x. And as you can see, this looks similar to log x of the previous page, okay, with the same domain, 0 to infinity, the same range, negative to positive infinity, same vertical asymptote, x equal to 0. Let me just, okay, again, and the x-intercept is at 1, 0. So y equals ln x. Again, the y-intercept, so the domain, I'm going to write d 0 to infinity, range negative to positive infinity. VA is the y-axis having equation x equals 0. So that's general, everybody. Let's graph y equals ln of minus x, which means reflected across the y-axis when you change the x to minus x. So this flips over, looking like that. So the x-intercept was located at 1, 0. Now the new one is at negative 1, 0. Everything else is almost the same, meaning the range doesn't change, the vertical asymptote doesn't change. The domain was 0 to infinity, but the domain is negative infinity to 0. So the domain has changed for this guy. Okay, so you know, for this one, the domain is no longer 0 to infinity, but rather minus infinity to 0. Now, 2 minus x means minus x minus 2. So as far as this one is concerned, this is shifting to the right by 2 units. So we have this graph, then we have this one, and now we're going to shift it 2 units to the right. So this moves this way to the right by 2 units, looking like that. So as a result, the x-intercept 1, 0 move to negative 1, 0. It moves back to 1, 0. But it does change the domain and the vertical asymptote. So this point goes back here, minus 1, 0, 1, 0. Okay. Here's the new vertical asymptote. You can even, if you set this equal to 0, x equals 2 is your new vertical asymptote. For the end behavior, now the domain, again, I'm going to go back to this 0 to infinity. For this one, let me write the domain for this one is negative infinity to 0. And now since we shifted to the right by 2 units, negative infinity to 2. The range for all those three functions hasn't changed. It covers all the y-axis. So the vertical asymptote for these two is the same, but the vertical asymptote is different for this guy, x equals 2. So as x goes to 2, g of x goes to negative infinity. More specifically, 2 from the left, I'll show you. As x goes to negative infinity, notice x goes to negative infinity, this blows up to positive infinity. By g of x, we mean the y coordinate. And again, it's important to know when we say 2, 2 from the left, everybody. 2 from the left. Now, state the domain, vertical asymptote, and the end behavior of this function, h of x minus log 3x minus 4 plus 3. And again, we start with the basic function, namely log. So y equals log x, looking like that. Again, it doesn't have to be necessarily to scale. As I mentioned, when y equals log x with any base larger than 1, simply looks like that, with the x-intercept at 1, 0, domain from 0 to infinity, ranges all real numbers, vertical asymptote is the y-axis or x equal to 0. So that's the basic one we start. Now, from log x, we're going to go to log 3 times x, which means a horizontal shrink by a factor of 3. So for example, 1, 0 shrinks to 1/3 0. That's the meaning of it. You look at this one, if I factor the 3 out, I get just this one. Look at this one. It's the same as 3 times x minus 4/3. So those are the new intercepts. And so I take a factor of 3 out. The reason I do that, because I want to make sure I understand there is a shift of 4/3 to the right. So this means shift right by 4/3. So this is the original one, this is the new one, and this shifts right by 4/3. As it shifts right by 4/3, Remember the x-intercept at 1, 0. Now it's 1/3, 0. We shifted to the right by 4/3. So we have to add 4/3 to 1/3, and we get 5/3. So this is the newest one. All right. So please understand this is identical to this one. Now we have this negative sign to work on. If you put negative in front of this, the graph flips over with respect to the x-axis. So reflect across the x-axis. So this one, the red one now flips over. And the result is that the x-intercept has the same coordinates, 5/3 and 0. So we are here. What is left? +3. So add 3, that means shift up by 3 units. So this guy moves up by 3 units, which means this point now has coordinates 5/3, comma 3. And to make sure we understand what we are dealing with, we want to work on this with a little bit more detail so everybody is clear as to what's going on. So this is the result. Again, we've factored out the 3, and it looks like this. This is the original x-intercept that has shifted. This is the vertical asymptote. And to find the vertical asymptote, you can set this one equal to 0 or this one equal to 0. You can see x equals 4/3. So what happens is that the domain is from 4/3 to infinity. The range hasn't changed from negative to positive infinity. The end behavior, when x goes to infinity, when x gets larger, y goes down to negative infinity. When x goes towards 4/3, y or f of x blows up to infinity. So we write as x goes towards 4/3, h of x goes to infinity. As x goes to infinity, y goes to negative infinity. It's going down here. And again, this is really not proper. The proper way of writing it is 4/3 from the right, because the function is not defined even on the. So we see in calculus, we don't write 4/3. We write 4/3 from the right. This doesn't mean, it just means to the right of 4/3, a little bit more or larger than 4/3.